So we are very happy to have Yishay Mansour with us today. He's a professor at Tel Aviv University and also works in Google. So I'm not going to name all the things that Yishay did because it is way too many things, but I can say a few words. So he was named as an ACM fellow in 2014. He's an associate editor in a number of distinguished journals. Um, he published over 100 journal papers and 200 proceeding papers in many different topics, ranging from machine learning, algorithmic game theory, communication networks, theoretical computer science, uh, uh, and he had a lot of graduate students in those areas. And we're very, very lucky to have him as a speaker. Go ahead, Yishay.
Thank you very much, Michal, for this kind introduction, and thank you for everyone for inviting me to give this talk. So the paper that I'm going to describe appeared in Colt, and it's called A Theory of Interpretable Approximation. It's a joint work with Marco Bersan, Nicole Cesabianchi, Emanuele Spozio, Shai Moran, and Maximilian Thiessen. So now the talk would really be likely like a two-part talk. Initially, I'd like to sort of talk more about the area. I know that many of you are aware of it, but hopefully it will also spark maybe later discussion about sort of various issues that I would come to talk about. So the general area, the motivation is of course ethical and societal challenges in AI. And this is a very hot topic, not only in research in AI, but I think sort of in society at large. So one example is sort of the EU has a special law. I think it started the draft about 4 years ago. I think the regulation went into effect less than a year ago. And the attempt here is to sort of to try and regulate AI and try to sort of set an agenda for it. And in some sense, sort of this is a very high level of what the EU Artificial Intelligence Act suggests. It sort of suggests a way of sort of splitting the various applications into 5 categories, from minimal risk to unacceptable risk. And they have sort of, on the one hand side, they have something that what should be done in those categories. On the other hand side, they have sort of a set of examples of what are sort of various applications that falls in those categories. And one thing that sort of bothers me significantly is that it's very hard to get a definition from those things. And I'm going to get to those issues again and again. And I think sort of the missing definition is a big issue here. While I love mathematical definition, an alternative definition could be a process where you certify your software or something like this. In some sense, even if you have an application and you want to know how to classify it, it's unclear, like what's the difference between something that is called deep fake and what is called manipulation of behavior. And the other issue is, of course, since it's left undefined and there is no sort of body that really sort of regulates it, there will be a tendency of sort of whoever has the application, companies, to downgrade the risk. And this is sort of not what we are after. As a whole, sort of when we're thinking about societal challenges, we're thinking about fairness, accountability, transparency. And later I'll be sort of more precise of what I mean about explainability and interpretability. But let's sort of stay with the very high level. Sort of the OECD has a special committee that draws AI principles So it gives sort of guideline to policymaker of how one should regulate and how one should think about the principle of AI. So probably the most related thing is sort of what do they say about transparency and explainability? So here is like trying to read what they really sort of suggest. They say AI actors should commit to transparency and responsible disclosure regarding AI system. To this end, they should provide meaningful information, appropriate context, and consistent with the state of art. You can keep on reading, but in some sense, my feeling when looking at it, okay, it's not a guideline. It's a bunch of words that are hopeful, and I think it does highlight to me the drawback of many regulators, definitely here in Israel, but I think also in the EU and the US, who are trying not to commit themselves. So in some sense, what we see is sort of, we see many words, we see sort of like a high-level agenda. If we go back here, commit to transparency. They're not even saying you need to be transparent. Responsible disclosure. It's unclear what they mean. Not only what they mean for the policymaker, but I think even if you ask them, okay, like is this system, does it obey your definition? I think usually the answer is that we have no idea, right? It needs to be consistent with the state of art. Okay, so what, one thing that I will sort of try to push in the talk today is that I believe that definitions are important. And we need definitions, not only that the definition will set the agenda, because some definitions are the wrong definitions. And if we don't start with definitions, we'll never be able to sort the good ones from the bad ones. So let me continue sort of in this sort of introduction. So why do definitions matter? So this is the place where I'll try to convince you that really definitions do make a difference. And sort of as a highlight sort of this talk would be sort of in this big pyramid, only talking about the explainability and interpretability, which is part of a general and a more general agenda which is related to transparency. So let's start with transparency. So what do I think about transparency? Here is the transparency that you see when you buy drugs, right? This is like an over-the-counter drug. I don't even remember what's the drug name, but you can see that part of the transparency is saying what are the side effects, warnings, what are the disclaimers, etc. Of course, it has also direction and other information. So when we think about it, transparency, when it comes to AI or even software at large, you can just give the code, right? But the question is, what can you do with it? So if I give you the code of ChatGPT, you can simulate it on any input. But I think you can hardly understand anything if I give you a large language model and ask you, what does it do? And even worse, if I ask you, why does it do the things that it does? So transparency, although it's highlighted almost everywhere, I think it's the wrong agenda to think about when we are thinking about the societal challenges. The fact that the software would be open would not make it simple and would not make anyone really accept run it as it is any better off. Okay. So the two things that I would like sort of to discuss in more details are explainability and interpretability. And this is sort of my way of distinguishing between the two terms, which are probably interchangeable if you just ask anyone on the street. So I view explainability as answering a question of why. So the why is really a question about the ground truth. So the why is asking, why do we believe, let's say, the user will not repay the loan? So we don't give someone a loan because we believe that he will not repay the loan. This is the question of why. If we think about the actionable part of the why, then the action is here is sort of what the user can do to change the outcome, that it will repay the loan. The interpretability is about our prediction model. So it's answering a different question of how. How did we derive the prediction for the user? This is more about our model rather than the ground truth that will happen in the future. So if you think about the actionable part here, so this is sort of what the user can do to change the prediction. So notice there is a big difference between changing the prediction and changing the outcome in the future. And I think the one way to think about those differences, at least for me, is thinking about a crystal ball. So suppose we do have a crystal ball that tells us the future. So using the crystal ball, we can sort of explain things about the future. But the interpretability part is not about the future, but about the present, about the predictions that we are making now. So I think sort of the crystal ball is really sort of what we hope in explainability. What we hope in interpretability is sort of an understanding of a mechanics of a prediction algorithm. So as I said, explainability is about considering the ground truth on the one hand, and interpretability is about the prediction. So the goals are very similar, but the objective is very different. The interpretability takes a model and just explains it one way or another. Explainability sort of needs to be tested when you look into the future. Interpretability is tested now on the prediction model. So what should be our goals? So I think the goals should be thought as thinking that we have a proof system, right? We are trying to explain or to interpret something. So first of all, we should want correctness, right? So whatever we sort of explain is correct. The second thing, this I think in some sense goes many times unaware, you would like to have soundness. Soundness means that you cannot explain two different things, right? You cannot explain that the person will repay the loan, and at the same time explain that it will not repay the loan, right? So the soundness of the system means that you cannot prove two contradicting facts. Completeness, I think, is also very important but this is more in a high level. Completeness really would say that we would like to be able to prove anything which is correct. So basically in explainability, explain for any user what is the outcome. So those three things almost appear regularly in any proof system. I think what we need also is something which is like robustness. Robustness here really would mean that if we slightly perturb the attributes, we would like the outcome not to change drastically. And finally, we would like to have simplicity, because we would like our explanation or our interpretation to be able to be much simpler than the model itself. Because if we just care about the first three, and we want to do interpretability, I can just give you the model, and the model does essentially everything. Okay, here is sort of one small example. So I assume that most of you are familiar more than me with the LIME, the local interpretation model of agnostic explanation. So the idea here is that you'd like to explain a point. This is like this red point here. But you have a very complex terrain. And what you're really doing is that you're sort of saying locally things are going to behave linearly. So I try to locally find a linear separator. I would want to balance the error of my separator, giving different weights to points, and the complexity of my hypothesis. Okay, this is in a nutshell. But essentially, okay, you can give different weights, let's say, to this red point. How much weight are you giving it? If you want to ensure correctness, then you would give it very high weight, but this means that you lose soundness. Because if you give the red point, a very high weight, then it means that if I put it a plus, you'll explain a plus, and if I put a minus, you'll explain a minus, and you lose soundness. If you lower it, then you might even lose correctness, because it might be that locally it's on the other side of this hyperplane. Okay, so already the definitions show you that they do impose something, let's say. Okay, and there are many other sort of techniques of doing explanation, Shapley value, anchor, etc. I'm not going to get into them. What I wanted to highlight here is sort of when we look in this prism of a proof system, we can already see that there are problems even with basic explanation. And when you think about explainability, when I think explainability, my first thought is that not everything is explainable. In fact, most things should not be explainable. In the real discussion is, what are we willing to sacrifice? So here is two examples that I personally like. Okay, so I like chess. And in chess, it's very clear that any mediocre chess program can easily beat any grandmaster, right? So when we ask to explain, it's not clear what are we expecting. Here is the wrong way of doing the explanation. If we say, okay, the program is saying that white is much better than black, you know what? Let's play against you. Let the program play against the grandmaster, and we'll see that it would win. Okay, we can do it, but it will fail on soundness, because if they switch colors, sometimes the program will also beat the grandmaster when it plays black, although it thinks that black should lose the game. So it's not clear what is really our expectation in explanation. Like in the recent trend, if people like when there are world championship in chess, it's very interesting to see how the interaction really goes. You see it on YouTube, you see the board, and then there's usually like two grandmasters doing the explanation, and at the bottom of the screen, you see as a running score what is the machine learning software suggesting. And a large part of the discussion between the grandmaster is trying to explain why is the machine learning suggesting why it is suggesting. Okay, so this is one example. I think another example, which is this for me amazing. This is like the eye retina sort of. So Google sort of built software to basically test and be able to recognize various fundos on the eye. This is the main goal there, is to get to third world countries where people do not have access to regular eye doctors, and then sort of do a test without any doctors and get a warning in some cases, and then sort of screen the people and send them to the appropriate healthcare. But once they had all those pictures of eyes, so they just ran just a small experiment. It's not clear to me why, but it sounds like a reasonable thing to do. They try to see whether they can guess the gender from the eye retina. The amazing thing is that they are way over 98%, right? Sort of. They can predict the gender from the eye retina, amazingly well. The unfortunate thing is it comes as a shock to eye doctors. They have no idea in what way an eye of a female and a male are different. Like although the software is able to use this information, so there is clearly something different, it's still a mystery how are those two things different. Okay, so again, sort of what do we expect here as an explanation? It's unclear. Okay, this is not my slide. This is so sometimes you sit in a talk and it hits you that you understand something. So this is a slide by a PhD student in Tel Aviv, but she's not a computer scientist. She is in the law department, and she was giving a talk about explainability in general, and then she put this slide and said, here is what computer scientists thinks about explainability. The crowd, which was almost unanimously, almost except for me, people from the law department, everyone laughed. And then I realized that in some sense, we can have our definitions, but we need to remember that there is something on the other side that expect other things from what is an explanation. And the fact that sort of anyone in the law department sort of seeing this slide with graphs and whatever, this is something that they definitely don't call an explanation, not ignoring how significant it is. Okay, let me sort of end this first half saying that there is hope. Okay, I'm apologizing that this is in Hebrew, but I'll explain to you what you're seeing. This is a sort of something that you get from the pension funds. I wasn't able to find something in English in different country. I think it took the regulator a few decades to make the annual report of the pension fund readable. So here you have like balloon that says, check whether the amounts of your insurance are adequate for what you need. And here it says, check the expense ratio that you are being paid. And this is sort of the average expense ratio in this fund from deposit and from savings. So this is sort of things that people should be aware of. Here is sort of how much will you get if you retire at the age of 64, in case of a death, in case of your child, etc. So I think the regulator did a great job over the years trying, like, the information was always there, right? So I got like 5-6 pages with numbers, and you just buried them somewhere because you had no idea how to read them. And I think there is a way of making things accessible. It does require the regulator to think a lot and to work a lot in iterations. And this is the case where I think the pensions funds were willing and interesting to make things accessible. Okay. So now, let me sort of start talking about the approximation and interpretability. So what was our guiding principle before we get to a definition? So interpretation of approximation, what we've thought about is a small aggregation of simple hypotheses. In small aggregation, the main way that we are going to talk about it is shallow decision trees. In simple hypothesis, we define it as having small VC dimensions. So this is sort of what we would like to get as an interpretation of a classifier. And approximability, the way that we'd like to think about it is very much like in the PAC model. We would like it for every distribution to be able to get a good approximation. It may require a large aggregation. So the main difference between interpretation and just approximation is how big is the aggregation, or how deep are the decision trees that are required. So in interpretability, we would like that for every distribution, we would have a bounded size good approximation. Just approximability, we don't care about the size, but we do want the error to go down to zero as we are getting larger and larger aggregations. So what are we trying to understand? We try to understand sort of the model complexity, taking the model as any reasonable measure, and trying in the accuracy sort of to see how, when we fix the model complexity, how are we trading off approximability and interpretability? And at a high level, to answer the question, when do we need more complex model? And how much are we benefiting from more complex model? Okay. Okay, so we need some definitions. So it's not going to be too many definitions. So this is much in line with the PAC model. Right? We have a domain X, we have a predictor that we like to explain. So C is a predictor, and what we would like is to approximate or interpret it. We'll have a hypothesis class. So this is the class H. So those would be for function mapping from the domain X to either 0 or 1. And what we'll be building decision trees over this class H. So notice that the splits, since the class H has binary labels, the splits are going to be binary, so we are going to have binary decision trees, and our complexity measure is going to be the depth of the decision tree. So what our objective, our loss function would be the classification error. So fixing it for any distribution T, we look at the probability that a tree misclassifies our predictor, right? So essentially what we would like to have is to get a tree that has a low 0-1 loss or a low misclassification error. Okay, for approximation, here is the way that we'll define it. So the intuition is that what we would like is for any distribution in any error epsilon, that there will be a good tree, but there is no limit on the depth. So the way that we define it is that we have an epsilon approximation with respect to a given distribution. Though this is the set of all trees whose error is at most epsilon. And the concept it would be approximable by H if for any distribution and any accuracy parameter epsilon, we have some tree. So the set of all trees of error less than epsilon is not empty. So we are not, so notice that it's not really realizability, because we are not assuming that the concept C can be represented by a decision tree, but it can be represented to an arbitrary accuracy. So this is the notion of approximation. For any distribution and any error rate, there is a tree whose error rate is lower than this, epsilon. Okay. Next, we would like to define interpretability. So interpretability, we would like to add the simplicity to the complexity. So we would add a depth bound. So first of all, we would like to consider the minimal depth tree that has error epsilon. So formally, for any error epsilon in any distribution P, what we are interested is the infimum over all decision tree of the depth of a decision tree. So this is like the decision tree that has the smallest depth and achieve error at most epsilon. And uniform interpretability we define as that the concept C is uniformly interpretable using a class of hypothesis H, if there exists a rate function, so f would be mapping from accuracy to depth of a tree. So it's going to be a rate function f, that for any epsilon and any distribution, the depth, we can sort of bound the depth of the smallest tree with epsilon error by f of epsilon. So think of f of epsilon maybe as 1 over epsilon squared, or the VC dimension over epsilon, or something like this. So it is, we are allowing in interpretability to get larger and larger tree as epsilon goes to 0, but we would like to have a uniform bound depending only on epsilon. So the uniform bound has to hold for all distribution and depends only on our error rate, epsilon. Okay, so this is a good point to pause and ask if there are questions. Okay, let me continue. Okay, so here's, I think this is the visual way of understanding the three definitions that we are going to talk about. Suppose we want to approximate a circle. So if we are going to approximate a circle using lines which are parallel to the axis, then we will get a high error, no matter how we try to explain it. So this is sort of the first case. In the first case, our hypothesis class H is not good enough, so the circle is not approximable by lines which are parallel to the axis. The second case is that we allow any number of lines, not necessarily sort of parallel to the axis, so we can always sort of using straight lines, but many of them get a very good approximation of a circle. And the third case is sort of, think what happens if we had a margin. If we guarantee you a margin, then we will be able to sort of explain, represent the circle using a few number of lines, right? So the first case is an example which is not approximable. The second case is approximable, but uses many hypotheses. And the third case, when we have a margin, it is interpretable and uniformly interpretable. Okay, so those are the three sort of classes that I would like to talk about. So the basic thing that we were looking at is motivating by distribution tree learning with the PAC model inspiration. How does the complexity or depth depends on accuracy? Like in the PAC learning, the complexity grows with the tree size. As trees become larger, the VC dimension become larger, and you get a sample bound that depends on the VC dimension, which depends on the tree size. But what happens if we are looking on the approximability and interpretability that I just defined? So surprisingly, any concept, any C that we'd like as our predictor, and any H that is a VC class, so has a finite VC dimension, we will have 1 out of 3 categories. The first one is C is not approximable by H. Remember this picture, this is the A here. The second one is that C is approximable by H, but not interpretable. So it means that I can get high accuracy as much as I like, but there will be distributions that will require me to get larger and larger tree, and I cannot bound the depth of a tree only as a function of the accuracy. And the third case is the uniform interpretability, that there will be a constant depth rate which will apply to any distribution. Okay, so the main thing that I would like to show you now is this theorem, but at the high level, this theorem says it's sort of surprising. There's only 3 cases. You cannot approximate, or you can approximate, but you cannot bound in any way. There are distributions that will make you require larger and larger depth, or there is a fixed depth, and this fixed depth holds for any distribution. Just as a comment, if we give up on the assumption of the VC classes, we at the third thing sort of what it will hold, but we sort of will need a slightly larger depth. Right? The depth would not be a constant, but will depend on the epsilon, right? Okay, so let's sort of dive in and do the proof here. Okay. So here's the proof sketch. So suppose one fails, right? So one fails, so it means that it's not the case that C is not approximable, right? So it means that for every epsilon and every distribution, there exists a tree of finite depth that has an error epsilon, right? So this implies that if we fix any gamma, one of the two cases should hold. Either for any depth d, there is a distribution that depends on the depth, such that any tree of depth d has a large loss, has a loss of at least a half minus gamma. What I'm going to show that in this case, the concept plus C is approximable, but not interpretable. The other case is that there exists a D such that for any distribution has a depth D which has loss a half minus gamma. Okay? In this case, I want to show that it is interpretable at depth D. Not depth D exactly, but it's going to be a function of D. Okay? Okay, so those are the two cases. So I want to show in the first case that it's approximable and not interpretable. And in the second case, I want to show that if for any distribution there is a tree with bounded loss, then it is interpretable. Okay. Okay, let's start with the first case. So the first case, what we want to show is there is a bad distribution by combining all, like we have for each depth a bad distribution, PD, for which we know that any tree of depth D has a high error rate. Okay? What are we trying to show? We are trying to show that there is no rate function that we can use. So let's think that fix a rate function, and then I'll show you that this rate is not big enough. So this rate could be, let's say, 1 over epsilon squared, or even exponential in 1 over epsilon, or whatever. Okay. And here is the basic idea is that I'm going to sort of take a sequence of error rates which are diminishing. So I'm going to take, like for every n, I'll take an error rate which is 2 to the minus n times this sort of basic error rate for which I know. Now, I'm assuming that I have this rate function, right? So I can look at what does the rate function give me for this tiny error, some depth dn. Right? So now I can combine all this distribution in the following way, right? I build distribution P star by sampling sort of the depth n from with probability 2 to the minus n, and then mixing the distribution which is defined for depth n. Right? So this is a valid distribution, just a mixture of the original distribution. Okay. So now by construction, I'm claiming that if I look at the depth that I need in P star, right, then it has to be, right, because this epsilon n is 2 to the minus n times a half minus gamma, and P star is going to select the distribution of dn with probability 2 to the minus n. So the depth right? So the depth of P star has to be at least the depth required by PDN to get a half minus gamma, right? Because this is the probability that I will select this depth. So what do I know for my assumption is that this distribution is bad. It's bad in the sense that it will require a depth more than dn. Okay? So basically I combined the bad, so where did I start? I start with sort of assuming that I have bad distribution, one for each depth. I combine them to one distribution. And I'm saying that in this distribution, if you have a bounded rate, then you would have a bounded rate, a smaller depth in this PDN, and this is a contradiction to the assumption. So really what I will show here is that in this case, no matter how you fix the rate functions, there is going to be some fixed distribution P star such that you will require, the P star will require depth which is more than the rate defined here. Questions? Okay, so we are done with the first part. And now I think sort of, this is sort of a less surprising fact. I think the next construction would be the more surprising, at least for me. So now I want to, okay, we are considering trees of depth D. And what did we assume? We assume that for any distribution over the input, there exists a tree of depth D that has a bounded error, an error at most a half minus gamma. So now we can sort of use the minimax theorem. There are a few details that I'll tell you more in the next slide. And say that there is a distribution over trees that for any input has a small expected loss. So this is sort of the way to think about it. It's a minimax theorem, right? So we had the supermum over distribution and the infimum over the trees of having the error, and we can switch them. So, and I'll tell you in a few, soon sort of what are the requirements that so the infimum should have been here. Okay, so here I have a typo. Never mind. Let's just stay here. Okay, so we will have a distribution Q over the trees, and for any input Ex, we will get the value of a gain, which would be a half minus gamma. Right. Okay, so what we need to sort of, I will show you in the next slide basically, that we can sort of do this and approximate the distribution Q by a big decision tree, but the size of the decision tree will depend only on the parameters D and gamma. And this will imply that it's interpretable, that there is a fixed depth which is independent from epsilon, from which we can explain things. Okay, so to use the minimax theorem, I need a finite set. So I want the duality of the linear program. I don't want something more complex. So just think that we just take a finite sample. And later we can argue that if we take a large enough finite sample, uniform convergence will imply that it holds also on the distribution. And the way that so remember, sort of now we are guaranteed that we have a distribution over trees of depth D, and I want to approximate this distribution. And I want to approximate it by using a few trees. And the way that I can do it, I can just sample trees from these distributions and then average them. And if I average enough trees, then I can sort of use the regular concentration bounds and argue that my approximation or my average is close to the expectation, and therefore the error rate is bounded at most by a half minus gamma. So essentially, we can show that there exists a set of trees of depth D And they would guarantee that anything in the final sample that we have, if we take the majority of the trees, the error is going to be it's going to be always correct. Because the majorities of the trees here are correct, so the majority would give us the true label for any x. So now we have a majority of R trees, each tree is depth D, so essentially we'll get a decision tree of depth D times R. So we can build one decision tree which is good for any epsilon. This gamma is unrelated to the epsilon. Okay? So any distribution has a good sample. This is like the basic theorem of the VC dimension. So essentially, in the second case, what we can show is that basically the rate or the depth of a tree is independent of epsilon. Right? Any distribution, it's not, right? We are able to build one tree, right? If you guarantee that every distribution has a good tree of depth D, I can show you one tree which is good for all distributions. Okay. Questions? Okay. In the paper, we have more results. We have also an algebraic characterization. You don't need to go through trees. You can sort of define things with countable unions and then do the closure of them. And again, you will get a trichotomy is very similar. Either things are not approximable or they are approximable if the concept is in the closure of the countable union of the sigma algebra. And C would be uniformly interpretable if you do the algebra of depth D and then do the closure. Okay? So this is an algebraic characterization. We can also define things with graded complexity of union intersection and a similar results apply. So the basic message of this slide is that while I talked about decision trees and advocated decision trees, it's not really about decision trees. It's really about having a bounded complexity and in what way are you composing things and how many times are you composing them. Okay, let me sort of, okay, it's good, we have 10 minutes. Let me try to write up. Okay. So one thing that I do believe a lot is that we need definitions, and the way that I look at our work is sort of, it's a starting point. We try to give a very formal definition of what is approximability and what is interpretability and how are they different. And the real hope is that this would initiate a discussion, especially between people like you, on interpretability and also about explainability. We are currently also working on trying to get things of explainability from a learning theoretic perspective. So, so what we would like to see is algorithmic approach and the respective guarantees. Maybe it's not clear that the VC dimension is really the way to go. Maybe we can get even a much better characterization of non-VC classes. And definitely we are interested in going beyond the binary case. And I think sort of explainability is sort of a real challenge. And in my view, the difference between explainability and interpretability is really that explainability needs to talk about the ground truth. Right? Here, we really sort of, in this work, started from a predictor, C, and build a decision tree using some hypothesis from a class H to explain it, to interpret it. Explainability would need a different set of tools because we are interested in talking about the ground truth itself. Okay. And thank you very much. And if there are any questions, I'll be more than happy to answer.